the whispers are getting louder in baseball. It's not just about the big contracts or the superstar trades anymore. It's about a deeper, almost invisible battle unfolding behind the scenes, the war over data. Are some franchises consistently outmaneuvering their rivals, not by accident, but by cracking a hidden code within the numbers? A code that reveals surprising truths about performance, investment, and ultimately, victory itself. For years, we've settled for comparing 2 teams, 2 players, 2 strategies. But what if we need to assess 3, 4, or even 5 different approaches simultaneously? What if we want to know if specific coaching philosophies, salary structures, or even new pitching regulations have truly distinct impacts across multiple groups? Stacking up endless head-to-head battles just leads to statistical chaos, escalating the risk of false conclusions that could derail a team's entire season. This is where traditional methods fall short, leaving crucial insights buried beneath a mountain of messy comparisons. This is precisely where Analysis of Variance, or ANOVA, steps onto the baseball diamond, offering a powerful alternative. Imagine trying to compare the average on-base percentage of players developed in 3 distinct minor league systems, one focused on traditional hitting, another on launch angle and exit velocity, and a third on pure athleticism. Instead of running multiple, error-prone pairwise comparisons, ANOVA allows us to test them all at once. It's like a single, decisive pitch that can strike out the ambiguity of multiple t-tests. Why is this so critical for front offices obsessed with marginal gains? Because with every additional t-test you run, the probability of falsely declaring a significant difference, a type 1 error, skyrockets. You might conclude that one minor league system is superior when, in reality, any observed difference is just random chance. ANOVA is designed to control this risk, providing a much more reliable framework for decision-making. In a league where every percentage point matters, avoiding statistical sabotage is paramount. At its heart, ANOVA compares 2 types of variation, the variance between the groups and the variance within the groups. Think about those 3 minor league systems again. If the average on-base percentage differs wildly between the systems, but players within each system perform very similarly, that suggests a real difference driven by the system itself. If, however, players within each system are all over the map, regardless of which system they came from, then any observed differences between the systems are likely just noise. This comparison is quantified by the F-Statistic. The F-Statistic is essentially a ratio \frac, \text, variance between groups, \text, variance within groups. A large F-Statistic, much greater than 1, indicates that the differences between your groups are substantial compared to the natural variation within each group. This suggests that the different minor league systems, or coaching styles, or even bat technologies, are indeed having a statistically significant impact. It's the moment the data begins to speak, revealing a pattern instead of mere randomness. Just like in other hypothesis tests, the F-statistic leads us to a p-value. This p-value tells us the probability of observing such an F-statistic if there were no real difference between the group means. A small p-value, typically less than 0.05, signals that our observed differences are highly unlikely to be due to chance alone. It's the data's verdict. There is a statistically significant difference somewhere among the groups being compared. This is the green light for analysts to dig deeper, confirming whether a strategy is truly effective. Let's consider a classic baseball debate. How do different ballparks affect home run distances? Imagine we collect data on average home run distances from 3 distinct stadium types: classic hitter-friendly parks, modern pitcher-friendly parks, and altitude-influenced stadiums. We use ANOVA to compare these 3 groups. The null hypothesis is that the average home run distance is the same across all 3 park types. Our alternative hypothesis is that at least one park type has a different average distance. The results could reveal unexpected advantages or disadvantages inherent to stadium design, impacting team roster construction and game strategy. If our ANOVA returns a significant p-value, we know there's a difference somewhere, but we don't know which specific groups are different from each other. That's where post-hoc tests come in. Think of them as follow-up investigations. After our initial ANOVA finds that different ballpark types do affect home run distances, a Tukey HSD post-hoc test might then pinpoint that classic hitter-friendly parks lead to significantly longer average home run distances than modern pitcher-friendly parks, while altitude parks are only significantly different from one of them. These tests refine our understanding, turning a general insight into actionable intelligence for GMs. This isn't just academic theory, it's the engine driving the modern baseball revolution. Teams are using ANOVA to evaluate the effectiveness of new training regimens, comparing player performance across different strength and conditioning programs. They're assessing the impact of analytic staff size on team wins. They're even dissecting how different pitch sequencing strategies affect batting average against. The insights gained from ANOVA are translating directly into competitive advantages, influencing everything from minor league development to multi-million-dollar free agent signings. The traditional scout's eye is now augmented, and often challenged by the cold, hard numbers. As data analysis tools become more sophisticated, ANOVA will only grow in importance, allowing teams to unearth even more subtle, yet significant, patterns. Could it reveal which player development pipelines consistently produce high-value talent regardless of draft position? Or pinpoint the optimal blend of veteran leadership and young talent for sustained success? The power to efficiently compare multiple variables simultaneously offers an unseen edge in a league where every team is desperately searching for the next breakthrough. The teams that master ANOVA aren't just playing the game, they're rewriting its rules, one data point at a time. The battle for baseball supremacy is now fought on spreadsheets as much as on the field. ANOVA is a crucial weapon in this silent war, enabling front offices to move beyond guesswork and anecdote towards data-driven certainty. It empowers them to ask complex questions, compare multiple realities, and identify the truly significant factors that separate champions from contenders. The game is evolving, driven by insights previously hidden in plain sight. Are you ready to see what the numbers truly reveal?